actually, if you want to deploy it for gamma equals 0.9 or 0.95, you actually train it for gamma equals 0.8 or 0.7. This actually generalizes well. So this is an interesting paper by Nan Jiang from his PhD thesis. I think Nan gave a talk here yesterday on a different topic. So that's, I don't know if people have looked into it much. So just one, I mean, if you use a smaller gamma, I guess there is an advantage, it'll converge faster. And if you have a small amount of data, it generalizes better. This is sort of the high level intuition, although I don't know the details of it. But apparently this is what people do in practice. So,
yeah, but here, this shows you don't need to.
Yeah, that's what I'm saying. The connection is, it's kind of interesting. Yeah. So it might be interesting to sort of compare that, or point out that it doesn't really, you don't really need to do, because I guess one question I've always been confused about is what gamma should you choose? I mean,
right. I think this work shows that it shouldn't matter. The discount factor shouldn't really.
Agree. That's interesting. Yeah.
Okay, so our next speaker, my old buddy from Illinois, Srikant, is boy. Well, I mean, so he's very well known in communication circles, expert in game theory, and if you go to his bio, I mean, his interests are so broad you can't even list it all. He's got some stunning awards, and he's a chair professor at the Department of Electrical and Computer Engineering in my hometown, Urbana-Champaign, and at the Coordinated Science Lab. I'll let you go, Srikant.
Thank you very much, Sean. Thank you for the invitation to come to this workshop, and it's especially an honor to be introduced by Sean. I was a graduate student when Sean arrived at Illinois, and he was one of my heroes, and it's delightful to be here, the session chaired by him. And it's also particularly interesting to be in the session where Sean gave a talk, and Anna was supposed to give a talk, and Aditya gave a talk, because some of my work in this talk, or the proof relies on some of the earlier work. So this is a paper that will appear in Neurips this year, and the title of the talk is The Mean Squared Error of Double Q Learning. I think all of you know what Q learning is, and probably some of you may have heard of double Q learning. So I'll talk a little bit about what double Q learning is and what we did to compare double Q learning and Q learning. So this is a joint work with Wentao Wang, who is this super amazing kid from Tsinghua. He was a junior when he visited me. He's just starting a senior year at Tsinghua. He'll be applying for grad school this year, and he already has 2 papers in Sigmatrix, 1 in Neurips, and he's probably already published more papers than many PhD students by the time they graduate. He's from the Yao class, which you probably know what the Yao class is at Tsinghua. And Harsh Gupta, my PhD student who just graduated, Niauha, my colleague, who's actually moving to ETH Computer Science Department next week, and Lei Ying from the University of Michigan. So I guess I won't give much of an introduction. I think in this audience, everybody knows what we are dealing with. So we have a dynamical system, and we're interested in this particular talk, I'm interested in maximizing a reward, which is a discounted reward, infinite horizon discounted reward. And I think we all know the Q-learning algorithm. So we have the Bellman equation for the state action value function Q, and if the conditional expectation can be calculated. So when I was in grad school and when people used to teach stochastic control, I guess we used to assume everything was given, and we used to figure out, we were told that this is a contraction mapping, so you can just recursively solve this. Of course, these days, the cool thing to do is, of course, assume that you don't know the probability transition matrix. And so you want to try to solve this from a trace or from simulation data. So one thing to point out here is, so there have been many techniques which have been studied over the years to improve the performance of Q-learning. And in particular, double Q-learning is one of these techniques which looks at the bias, sort of, I'll talk about it in the next slide, as to, when we are estimating this max from empirical values of Q. What we are really interested in is max of the expected value of this quantity, but we only have empirical estimate of Q, and so we are trying to do this. And so the question is, how badly, or what is the impact of doing this? And here's an interesting example. I think this problem was first identified by Hado van Hasselt in a 2010 NeurIPS paper. And this example in Sutton and Barto's book sort of gives a very nice explanation for what's going on here. So let's say you're in state A. So if you go to the right, you get a reward of 0. But if you go to the left, you get a reward of -1. It doesn't matter what action you take. There are a bunch of IID random variables. The reward for each of those transitions is a Gaussian random variable with mean -0.1 and variance 1. And so you get a negative reward if you go to the left. But on the other hand, what does Q-learning do? Q-learning operates using an estimate of these quantities, right? So it's possible that the maximum of these quantities is positive. So and you'll keep going to the right initially. So the question is, how long does it take for Q-learning to learn to go to the right? But in reality, it'll start going to the left initially for a long time. I mean, we know from Q-learning convergence theory that this will eventually converge, at least in the tabular case. But if you look at the, so what Sutton and Barto plot is, look at the number of episodes and how often do you go to the left? Okay, so that's what's plotted on the y-axis. And if you look at Q-learning, initially, actually, it goes to the left a lot. Okay, and gradually it learns to figure out you should go to the right. Okay, so the question is, can you fix this problem? Can you figure out, can you do something about this maximization bias, as they call it? So here's the intuition. And of course, what is implemented is a heuristic. So here is an intuition. So the idea is that you want to estimate the maximum of the mean of a bunch of random variables. And let's say you have 20 samples each from each of these random variables. One way to estimate the max of this quantity is to just take the empirical mean of each of the random variables and just take the max. Okay, let's just say for simplicity, you have 20 samples. Another way to do it would be to divide the 20 samples into batches of 10 each. Okay, so you take the 20 samples, take just 10 of them, and use them to estimate the empirical mean. Okay, and then find whichever random variable has the largest mean from this empirical estimate. And then estimate max of I of expected value of yi by computing the by looking at the empirical mean of I star. Okay, so this is the second way to estimate it. So I hope everybody understands. The first way to estimate this is just simply looking at all the samples. The second way to estimate it is that divide it into 2 batches, use one batch to figure out which the maximum is, and then estimate the mean of that maximum. Okay. So what Van Hasselt argues is that the first estimator overestimates and the second estimator underestimates. And so he suggests using something motivated by the second estimator, because these are not IID random variables. I mean, Qs are just estimated using stochastic approximation. So here's the heuristic that he suggests. So traditional Q-learning is this. So you have a single estimate of the Q function, which you're using in the right-hand side. So basically, if I take the Q here and move it inside the alpha, basically you're comparing Q with itself in the future, right? Whereas what Van Hasselt suggests is that the simple IID example suggests that actually your actions should be separate from your estimator. So what he says is that, what we should be doing is we should have 2 estimators. One, which is used to figure out what your optimal action is in the next stage. And when you're using the Bellman error comparison, you have to compare it to the other estimator. So this is just purely a heuristic motivated by the discussion in the previous page, which was also provided in his paper. And so basically Q-learning takes more space in the sense that because you have to maintain 2 Q estimates. But in this example in the Sutton and Barto paper, so this is called double Q-learning, by the way. So it's called double Q-learning because you're maintaining 2 estimates of the Q value. Double Q-learning actually dramatically improves the performance of Q-learning. Okay, and this has been studied in a lot of examples. So the original Van Hasselt paper was for tabular Q-learning, and then people have used it in for large scale stochastic control problems where you're estimating the Q function using deep neural networks and so on. And I visited companies where people use double Q-learning, and they tell me that it converges much faster, and it also leads to some stability. I mean, it makes when you have a neural network in the loop, it actually makes the convergence of the neural network training part better. It's basically what I've heard anecdotally. But it's also not difficult to come up with examples where the maximization bias doesn't matter. Let's go back to the Sutton and Bartow example. Suppose I replace one of these quantities, one of these rewards by n.51. So in this case, going to the left is the optimal thing to do, because there is an action on the left that gives you a positive reward, whereas going to the right gives you 0 reward. So yeah, so according to Van Hassel's paper, there will be a maximization bias, but the maximization bias doesn't affect us. You're actually going to the left is a good thing to do in this case. So you can come up with examples where actually Q-learning performs better than double Q-learning. So one of the questions we were thinking about was, is there a way to actually make double Q-learning perform as well as Q-learning when Q-learning performs well, but then it also improves the transient performance when Q-learning does not perform well. And one of the things we observed also is that in these cases where Q-learning performs well, it also performs well in terms of asymptotic mean squared error. So this is the connection to Aditya and Sean and Chen and Anna Busich's work. So we thought, okay, why not compare the asymptotic mean squared error of Q-learning and double Q-learning and try to understand under what conditions and how do we choose the step size of double Q-learning so that it matches at least the asymptotic mean squared error of Q-learning. In all the examples that we tried out, it seemed like double Q-learning seemed to have worse asymptotic performance, even though sometimes the transient performance is much better. So we thought maybe if we can match the asymptotic mean squared error, and then hopefully those same set of parameters, if it also works well for transient, which we cannot, transient analysis, which we don't know how to do, then maybe there's something interesting to learn here. So that's sort of the motivation for this work. So our goal is to use asymptotic mean squared error as a metric, and I put some question marks here because I know we all use asymptotic mean squared error, but people, always complain saying that you're not really as interested in estimating the Q function. You're really interested in learning the optimal policy, and I think Aditya touched upon this in the last talk a little bit. And so the question, but I don't know any other metric to compare, so I'm going to use asymptotic mean squared error and derive conditions on the learning rates so that double Q-learning at least has the same asymptotic mean squared error as Q-learning, and then experimentally check, how does this learning rate compare? Okay, so I haven't tried ZAP Q-learning or whether there's an equivalent of ZAP Q-learning for double Q-learning and so on. That's an interesting question that I haven't addressed here. So motivated by this paper by Devraj and Main, and you can go look at that paper for conditions. So basically, I'm not going to look at Q-learning. I'm just simply going to look at TD learning. And so you assume a fixed policy, and then you compare double Q-learning, double TD learning with single TD learning. But of course, then the question is which policy should you use to compare? Because the comparison makes sense if we use the optimal policy, but since we don't know the optimal policy, how do we compare? But we establish a result that holds for all policies, and so it will also hold for the optimal policy. And we'll use linear function approximation in this talk. Of course, we've done some experiments with neural networks, but that's just a heuristic. So we'll use linear function approximation for this talk. So in other words, we're approximating the value function, as we all know, as some theta transpose phi, where phi is a known feature vector whose dimension is typically smaller than that of the state. And this is Sutton's famous TD learning algorithm. So basically, you look at the error in the Bellman equation and then move it along the direction of the feature vector. You move theta along the direction of the feature vector. Okay, of course, the special case here is that if you use a vector with all zeros except in one place, then it reduces to tabular TD learning. Of course, Tsitsiklis and Van Roy pointed out and successfully utilized the property here that if you look at it as a function of theta, it's a linear function. So this is a special case of what one might call linear stochastic approximation. So you can write it in the form theta k plus 1 is theta k plus epsilon times some a, which is dependent on the underlying Markov chain, times theta k plus b of xk. And so if a bar, the expected value of a in steady state is Hurwitz, then this equation will be well behaved and you can study its properties. So if you write double Q-learning and remove the max from the equations, then this also is linear in the parameters theta a and theta b, right? So one can also use linear stochastic approximation results to study double TD learning. And so all I'm saying in this page is that you can now also write it in the form of a linear stochastic approximation, and you can study the asymptotic mean squared error of linear stochastic approximation, which has a long history going back to work on stochastic approximations. There are results in Benveniste and his co-author's book, and recently Chen, Devraj, Busic, and Main further analyzed this in the context of reinforcement learning. So I'm interested in the asymptotic mean squared error. So that's for TD learning, it's just simply, as Aditya had already mentioned, it is k times expected value of theta times plus theta k. I'm just going to assume theta star is 0. If theta star is not 0, you can just subtract that. And for double TD learning, there are two estimates. Or for double Q learning, there are two estimates. And you can also, instead of outputting the estimates, you could also take the average of the two estimates and use that as your output. So we are interested in comparing these three quantities to this quantity here. And of course, these two are of course going to be equal. So I can just think of, because it's symmetric. So I guess, yeah, so in double Q learning, there are two estimates that you maintain. And of course, by symmetry, the asymptotic mean squared error of the two of them will be the same. So really, we are interested in this one, and this one. Okay. So our main result is that if you use twice the step size of standard Q learning in double Q learning, then the asymptotic mean squared error of double Q learning, where you take the average of the two outputs, exactly matches that of Q learning. So if there are cases where you're worried that by using double Q learning, you might actually do worse, it doesn't happen if you use twice the step size for double Q learning. And of course, if you use only one of the outputs of double Q learning, you can actually prove that the asymptotic mean squared error is strictly less. Okay. So if I have time, I'll give some intuition as to why this is true. But first, I'll just give some examples. So this is a well-known example. This is Baird's example, where he came up with this example to show that Q learning with function approximation may not converge. The details of the example are not important. So here we have double Q learning. I mean, we have a lot of plots in the NeurIPS paper comparing it to Q learning, double Q learning, various other algorithms. But just for simplicity for this talk, if you want to look at the NeurIPS paper, you can get more information. And here's our proposed step size rule. And you can see that it seems to perform better. So this must be an example where Q learning actually does better. And so basically by doing this, doubling the step size, you actually get better performance than the double Q learning. So this is another example. This is grid world. Basically, you have to go from S to D, and then there are some rewards associated with the actions, and there's some probability of moving depending on what action you take. And the previous example was a linear function approximation example. So here's an example with tabular Q learning, and here again with our step size rule, DQ with averaging performs better than DQ with twice the step size, especially initially. And here's an example even asymptotically, where saying we increase the number of samples, double Q with averaging, you average the output, and using twice the step size actually gives much better performance in DQ. And the NeurIPS reviewer suggested doing some more examples with neural networks and so on, which we have done some of that. And the basic idea seems to continue to hold, although we haven't done Google-sized examples. I guess we haven't done very large examples with deep neural networks and so on. Okay, so in the remaining time, I will give some intuition as to why, how we did the comparison between double Q learning and Q learning. Even so, basically, it is well known that if you have a stochastic approximation algorithm of this form under some conditions, the asymptotic variance or asymptotic mean squared error satisfies this Lyapunov equation. Okay, where A is the expected value of this quantity. Now, as I mentioned earlier, standard TD learning can be put in this form. So you can use the same expression in the previous page to compute the asymptotic mean squared error. Or okay, so this is asymptotic. This is a covariance form. To compute the mean squared error, you will take the trace of this matrix, right? So the covariance you can compute for standard TD learning, and it'll satisfy some Lyapunov equation. And similarly for double Q learning, you can write, you can figure out what the Lyapunov equation. But the problem is these are complicated equations with no closed form expression. So the question is, how do you compare the performance of Q learning and double Q learning? So the first thing to notice is that because of the symmetry of double Q learning, the double Q learning maintains two estimates in QA and QB, and they're basically symmetric. One thing I forgot to mention is that you flip a random number, a Bernoulli random variable, and then if the Bernoulli random variable comes out 0, then you update the first one, otherwise you update the second one. But nevertheless, it's symmetric. Asymptotically, both of them will have the same covariance. So therefore, for double Q learning, there is a particular structure into the covariance matrix. That's the first thing to notice. And the second thing to notice, if you look at the A matrix for single Q learning and double Q learning, you will notice that the A matrix for single Q learning, if you call that A2 minus A1, meaning the first term I'm calling it A2, and the second term I call A1, the A matrix for double Q learning actually involves exactly those terms, except put it in some funny order. So the matrix for the A matrix for double Q learning is minus A1, A2, A2 minus A1 times half. Okay. So there's a lot of structure that allows us to compare the solution of this Lyapunov equation and the solution of this Lyapunov equation. And so if you just use this structure and do some manipulations, you can see that if the covariance of the double TD learning has this form, then you can show that V plus C over 2, these two terms averaged together, will be equal to the covariance of the single Q learning estimator. I mean, so this is all, even if it doesn't make sense, what I'm saying, essentially what I'm saying is that there is a structure to the linear stochastic approximation underlying Q learning and the linear stochastic approximation underlying double Q learning. You can exploit that structure to get some relationship between the solutions of the Lyapunov equations for TD learning and double TD learning. And now basically to compute the mean squared error, you have to take some trace and so on, and then some manipulations, some very simple calculations. But I think the clever thing was that Wentao noticed was actually to use this structure. And so what you can prove is that the asymptotic mean squared error of the average output, meaning if there are theta A and theta B are the two outputs of double TD learning or double Q learning, and then you take the average of that, and then that has the same asymptotic mean squared error of a single Q learning. But more importantly, this is a much trickier thing to prove. We can actually show that if you use one of the outputs of double Q learning, it'll strictly be, its asymptotic mean squared error will be strictly worse than that of just Q learning, just doing Q learning alone. And to do that, you have to show that trace of V is larger than trace of C, and that's a much more involved calculation. So I will wrap up here. I planned to talk for 25 minutes, and so I will do that. So we showed that an average estimator of double Q learning with twice the step size has the same asymptotic mean square error of Q learning. And the motivation was, as I mentioned earlier, double Q learning works very well in cases where there's this thing called the maximization bias, but you can easily come up with examples where the maximization bias doesn't hurt you. And in those examples, Q learning can sometimes do better. And in all of these examples, Q learning seems to, at least in the examples that we have tried, of course, it's not a proof, it's proof by simulation. Q learning seems to have better asymptotic mean squared error than double Q learning, although double Q learning seems to have typically better transient performance. So the question was, can we come up with a step size rule for double Q learning that will match the asymptotic performance of Q learning? And we did that. And then, of course, the next question was, does it actually hurt the performance of double Q learning in the transient phase if you use the step size rule? And at least in simulations, it seems to not hurt. So that's all we can say at this point. So this provides a possible step size guideline for double Q learning, and it's kind of interesting. I mean, these previous two talks made me think, maybe there's something else also one should be doing, such as ZapQ learning, and whether there is a version of ZapQ learning for double Q learning. And there are other things. I think there's something called target TD learning and target Q learning, which also improve the performance. All of this basically try to get at the fact that in Q learning, we are working with estimates that are crude. I mean, at least for a long time, these will be very crude estimates of the Q value, and what can we do to sort of improve those crude estimates? And so there's target TD learning. There's something called dueling, Q learning and the double Q learning. We just focused on double Q learning for no particular reason, and we were able to analyze it. But as I mentioned earlier, one interesting question I think that practitioners ask is, what is the point of studying asymptotic mean squared error? Who wants to estimate the Q function anyway? You are interested in finding the optimal policy. That's a valid question, and it'll be interesting to do some transient analysis here and study nonlinear function approximation. Our results are all true for linear stochastic approximation. So nonlinear function approximation would be interesting to study. And maybe somewhere between transient analysis and asymptotic analysis lies finite time analysis. And I just actually came across this paper, which is also going to appear in Europe's. So Shang, Zhao, Liang, and Zhang. Liang is also another grad student who was a grad student when Sean was a professor. She's Yingbin Liang, who's at Ohio State, and Sean was a professor at Illinois. So Yingbin has this paper with her co-authors on finite time analysis of double Q learning, where they, instead of looking at asymptotic mean square error, they try to get an expression or upper bound for the mean squared error for any time. And I haven't looked at this carefully, so I don't know what interesting information that might shed on the problem. Our goal was not to just study Q learning. We wanted to understand, can we sort of get at the benefits of both Q learning and double Q learning by looking at asymptotic mean squared error, whereas their work seems to just primarily study double Q learning, but it might also be, I don't know if you then compare it to other results on asymptotic or finite time analysis of single Q learning, maybe that'll also shed some light on what I'm talking about today. That's it. Thank you.
Nice work.
Thanks, Sean.
Any questions out there? By the way, I think maybe not ZAP, but the relative double Q.
Relative double Q. That's right. Relative double Q is what.
There'd be too much overhead with ZAP.
Correct.
But,
correct.
Yeah, but what's the step size? Maybe it's something I missed. You had a.
So it's G over n plus 1 for so this is true for any G, whatever appropriate G you choose for Q learning, G over n plus 1. And if you use 2G over n plus 1 for double Q learning, it matches the asymptotic covariance. It's kind of interesting.
Yeah. It almost feels like the average of theta A and theta B would satisfy their own third Q learning equation.
Exactly, yeah. Something like that. Except that because these are not IID random variables, it's kind of complicated. You can only it through the intuition. If everything was IID, then it's obvious. But if it's not IID, you have to go through this complicated Lyapunov analysis to understand it. We don't see a simple way, although intuitively that's what it seems like it is.
Yeah, the correlation.
Yeah,
that's right. If you don't have IID flipping back and forth, it'd be impossible too.
Yeah, that is another thing. But I'm saying that, but the correlation that the Q function estimator itself is not just a standard law of large numbers, but it's like some sort of asymptotic law of large numbers, and so that's why we go through this route.
It's remarkable that the coin flipping doesn't hurt you. That would seem to be a loss.
Well, the coin flip doesn't hurt you if you do the average. Yeah, if you do theta A plus theta B over 2. But if you just look at one of them, the coin flip hurts. If you just if you just look at one of them, actually you can prove strictly it's worse than Q learning.
Yeah, but it's surprising you can get rid of it so easily. That's cool.
Yeah.
That is really awesome.
Yeah, thank you.
And
I guess there is some question now. I don't know for whom.
Oh yeah. There's a Q&A there, right?
Is it useful to go triple Q learning?
Triple Q. All right.
That is an interesting question, actually. When my student gave this talk in his defense, Harsh Gupta, Bruce Hayek, my colleague, asked exactly the same question. Why not use triple Q learning? I think the idea is that you're basically increasing the storage by doing double Q learning. You have to store twice as many values. So you could do potentially triple Q learning, and then instead of using a Bernoulli random variable, you can use a random, you can decide to flip a coin to figure out which one you're going to update. So potentially it might help. But what is unclear to me is how do you do so let me quickly show you what double Q learning is. So one thing that is not obvious is that here when we are updating the equation for QA, we use QB. When we are updating the equation for QB, we are using so I don't know what happened. Sorry.
Yeah.
So it's not clear when you have 3. I don't know what you will compare here. I guess that maybe you could take the average and compare. I don't know. So one has to think a little bit about how to use triple Q learning if you were to use triple Q learning. But that is an interesting question, and somebody else asked the same question.
There's more questions are coming in. Let's see.
Okay.
So there's another one here. Yeah.
Can someone adaptively?
Thank you. I wanted to ask that too. I had the same question just now. Yeah.
Argadeep worked with Vivek Borkar, so.
Okay.
I don't know, Argadeep. I don't know. It's a good question. That's a interesting question. I remember Ben talked about. I heard him give 2 talks on this topic where you have multiple Q networks that you train, and then you keep switching between them. And I can't remember what it was. It was an Allerton plenary that he gave. So I don't know. Maybe it is related to that. I don't know the answer to the question. It's a very good question. Yeah. Do you know Aditya?
Yeah. So that's actually, I think, completely different sort of view. So that's like if you're doing Thompson sampling in a bandits problem, you have a posterior, and then you try to sample the Q function from this distribution. So they're maintaining multiple Q networks to essentially use it as a posterior on the Q function, instead of having a single Q function. So that's more of an exploration problem than.
I see. And then they use something like a Boltzmann exploration based on those Q functions.
So the sampling itself is the exploration. So they sample one of the Q functions. Let's say you have like 10 networks.
Okay.
You sample one of them, and then you be greedy with respect to one of them.
I see. But then you keep changing that?
Yes, in each of the episodes, you sample one of the
okay.
It's like a particle filter kind of a thing. So
I see. Okay, so that's a completely different motivation.
Yeah.
But it won't address this maximization bias that I'm
yeah, I don't know if they're related, but the motivation there is different. Yeah.
Okay. But this is also interesting. So this motivation is kind of from the IID case, but it somehow seems to work for Q learning. So it'll be interesting to understand, to make this motivation more precise for Q learning. Yeah. And there are places where Q learning does seem to work better. So it's not clear how to, but you're right. I mean, I guess Argadeep's question is valid. So is there a way to sort of switch between the two in some way? Yeah.
So, okay, well, I guess.
So I guess there's another question. Any ideas for doing some functional approximations? We did our whole analysis is for linear function approximation. For nonlinear function approximation, I don't know what to do at this point. I don't know if Sean or Aditya has some.
Well, yeah, but I think. Well, should I answer or should you, Aditya?
You can answer. I actually had a question. I'll just ask this to Srikant. So this Baird's example, it's supposed to be a counterexample. How did it converge? I mean, I saw that.
I think we chose gamma smaller than what it was.
Okay. So the counterexample is for particular gamma. Okay. Sorry. Yeah. Sean can go ahead. Sorry.
But it's an equivalent question. So basically, the asymptotic covariance for like Q learning is basically the same as looking at the linearization. And that's right. For that you have to analyze TD learning with off-policy TD learning.
That's true, and linearized.
So the question is, can you get a similar theory for off-policy TD learning? And I wonder if you can.
That is an interesting question. I don't know.
Because it's if and only if, basically. I mean,
right.
Once you can justify the linearization, which you know.
Right. But at least you can heuristically do the linearization and see, how it.
Yeah. So, do you think there's any hope for doing the off-policy?
Well, I mean, I guess what we are saying is that if it is linearized, if you use double the step size, it definitely both have the same. So if you do linearize it,
but it's off-policy. I mean,
it's off-policy. Okay.
Yeah, I don't think in general it converges. So
right. Off-policy. So basically, what you're saying is you use one policy, but then, that's right. If you use one policy, you use basically some trajectory generated by a policy, but then do your Q learning on that policy. So and I don't know. That's a tricky question.
Yeah, no, it is true. It's a hard question.
There is something called some other versions of TD0 that Bhatnagar has analyzed, who was Borkar's student. He analyzed with Sutton. He analyzed a bunch of versions of TD0 trying to get at off-policy TD.
GTD0 and GTD.
That's awful. Yeah.
That converges.
Yeah, that's true. But that's really.
Yeah, it converges, but it has like very high asymptotic variance. So that's what I think.
Okay. Sorry, I'll stop sharing.
Okay, cool. So everybody out there, it's mandatory to come to the panel. You're allowed to have a break. You're allowed to have a break now until whatever it is. Is it noon? I mean, well, anyway, for 30 minutes.
Yeah, 25 minutes. Yeah,
25 minutes. And come to the panel. It's going to be great. It's going to be a nice collection of panelists, and it'll be fun. And we'll free margaritas for everybody.
We'll hold you to it, Sean.
Okay. All right.
Okay, see you in a bit.
Okay, see you.